In Episode 8, titled IPv4 Addressing Strategy, Public/Private, Static/Dynamic, and Design Implications, we treat addressing as a foundation for control and routing because many network decisions become easier when your address plan is intentional. The exam often presents addressing as a background detail, but in practice, it is one of the strongest signals you can use to enforce zones, understand traffic, and troubleshoot quickly. A clean address strategy reduces ambiguity, helps segmentation, and supports reliable growth, while a messy strategy forces you to rely on brittle exceptions and tribal knowledge. Addressing is also where design meets reality, because you cannot route, filter, or log consistently if your addressing plan does not reflect how the environment is actually structured. The goal here is to build a practical mental model so you can choose the best answer when the scenario hints at addressing constraints. Before we continue, a quick note: this audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A key starting point is understanding public versus private ranges and typical placement patterns today, because the question often expects you to know where each belongs without turning it into a memorization contest. Public Internet Protocol version 4 addresses are globally routable, meaning they can be reached across the public internet when policies allow, and they are usually assigned by service providers or managed within cloud allocation constructs. Private ranges are not globally routable, meaning they are intended for internal use, and they are commonly used for internal workloads, internal clients, and segments that should not be directly exposed. Typical placement patterns follow a simple principle. Public addresses are used at controlled exposure points, such as internet-facing services and gateways, while private addresses dominate inside trusted and screened zones. This pattern supports segmentation because it creates clear boundaries between what is exposed and what is internal. On the exam, when you see phrases like internet-facing, public access, or external clients, you should expect public addressing at the edge and private addressing behind it. Static assignment has clear benefits for servers and infrastructure components because stability and predictability reduce operational risk. A static address means the same Internet Protocol address is consistently associated with a system, which helps when other components depend on known destinations. Infrastructure components like gateways, directory services, monitoring collectors, and critical servers often benefit from static addressing because it supports clear routing, firewall policy, and dependable logging correlations. Static addressing also reduces the chance that a critical dependency changes unexpectedly, which can create silent failures that are hard to diagnose. In many environments, static assignment is less about convenience and more about making control planes and core services reliable. For scenario questions, static addressing often aligns with workloads that must be reachable consistently, must be referenced by policy, or must support predictable operational processes. Dynamic assignment has strong benefits for clients and elastic workloads because flexibility is often more valuable than permanence in those contexts. Dynamic addressing means Internet Protocol addresses are assigned as needed from a pool, which supports turnover, scaling, and temporary instances without manual coordination. For end-user clients, dynamic assignment reduces administrative overhead because devices come and go, networks change, and manual assignment becomes a source of conflicts. For elastic workloads, dynamic addressing supports scale-out patterns where instances are created and destroyed based on demand, and it avoids wasting time managing addresses that may live only briefly. Dynamic addressing also supports automation because systems can be deployed rapidly without waiting for address coordination, which matters in modern environments. In exam terms, dynamic addressing often matches scenarios where scale and change are expected, where the workload is not a fixed dependency, or where automation and elasticity are emphasized. Subnet boundaries are one of the most powerful design tools you have because they let you match addressing to zones and blast radius goals without adding complexity. A subnet is not just a technical construct, it is a boundary that can reflect trust levels, function, or ownership, and those boundaries influence routing and policy enforcement. When you align subnets with zones, you create a natural mapping between address space and security intent, which makes segmentation and logging easier. Blast radius goals are about limiting how far a mistake or compromise can spread, and subnet boundaries help by restricting broad reachability and enabling tighter filtering. If everything is in one large subnet, controls become coarse, lateral movement becomes easier, and troubleshooting becomes more ambiguous. When subnets reflect zones, you can reason quickly about where traffic should and should not go, and that clarity is exactly what the exam often rewards. Address planning for growth, mergers, and multi-site expansion is where a good design shows its value, because the worst addressing problems often appear years after the first decision. Growth changes address consumption patterns, and plans that barely fit today often become emergencies when new teams or new services appear. Mergers introduce another environment with its own address choices, and integration becomes painful when both sides use the same private ranges without coordination. Multi-site expansion adds routing complexity, and address plans that are not structured can force awkward readdressing or brittle translation layers. A resilient approach is to leave room in each zone, keep consistent patterns across sites, and avoid fragmenting the address space into hard-to-summarize pieces. In exam scenarios, when the prompt hints at expansion, acquisition, or adding locations, the best answer usually reflects future-proofing rather than a plan that only fits today. Network address translation is a common supporting concept because it affects addressing, logging, and troubleshooting effort, and the exam often expects you to account for that operational impact. Network address translation changes address visibility across boundaries, which can help by reducing public address consumption and by hiding internal structure from external view. The trade-off is that translation can complicate troubleshooting because the address you see in logs at one point in the path may differ from the address seen elsewhere. Network address translation also affects how you correlate events, which matters for security investigations and compliance evidence because you need enough context to tie actions back to internal sources. When many internal systems share a translated address, you must rely on additional data like ports and timestamps to differentiate sessions. In scenario reasoning, answers that introduce network address translation should be evaluated not only for connectivity benefits, but also for the logging and operational discipline required to keep it manageable. Overlapping private ranges are a classic design hazard because they break peering and virtual private network designs, and they often appear as a hidden constraint in scenario questions. When two environments use the same private address space, routing becomes ambiguous because the same destination address could refer to two different places. Peering and virtual private network connectivity assume that address ranges are unique across connected networks, and overlap forces workarounds that add complexity and risk. Those workarounds can include translation or segmentation hacks that make troubleshooting and policy enforcement harder, and they often create brittle dependencies that fail during growth or change. The exam frequently tests awareness of this by presenting hybrid or merged environments and offering answers that ignore address overlap, which is usually a trap. The best answer typically acknowledges that overlap must be resolved through careful planning rather than pretending it will not matter. Consider an example choosing static or dynamic addressing for an application tier, because the distinction becomes clearer when you tie it to workload behavior. A front-end tier that scales out based on demand and is reached through a load balancing mechanism usually benefits from dynamic addresses, because individual instances are not stable dependencies. A database tier or a core service tier that must be referenced consistently and must support tight policy and predictable monitoring often benefits from static addressing, because stability supports control and operational clarity. Even within an application tier, supporting components like gateways, service discovery endpoints, and monitoring collectors often lean towards static addresses because other systems need consistent targets. The design choice is not moral, it is contextual, and the correct decision depends on how the tier is consumed and how it changes over time. In exam questions, the best option usually matches address type to the stability and dependency level of the workload, rather than applying a one-size-fits-all rule. A recurring pitfall is poor documentation causing duplicate Internet Protocol conflicts later, because addressing errors often hide until a new device appears or a new site connects. Duplicate addresses can create intermittent and confusing failures because traffic may sometimes reach the correct host and sometimes reach the wrong host, depending on caching and local segment behavior. In dynamic environments, duplicates can appear when pools are mismanaged, when reservations overlap, or when someone manually assigns an address inside a dynamic range. In static environments, duplicates often appear when records are not updated, when decommissioned systems are reused, or when multiple teams assign addresses without coordination. The technical fix can be straightforward, but the operational damage is large because it erodes trust in the network and consumes troubleshooting time. Scenario questions that mention intermittent reachability, new deployments, or recent changes often include addressing hygiene as an underlying factor, and documentation quality is part of that hygiene. A useful memory anchor is linking address type to workload stability level, because stability is usually the deciding factor you can infer from a scenario prompt. When the workload is stable, long-lived, and referenced by policy or dependencies, static addressing tends to support reliability and clarity. When the workload is transient, elastic, or replaced frequently, dynamic addressing tends to support automation and scale without manual coordination. This anchor helps you avoid the trap of choosing static addresses simply because they feel more controlled, which can actually increase operational burden in elastic environments. It also helps you avoid choosing dynamic addresses for core infrastructure that needs predictable targeting, which can create hidden fragility. In exam reasoning, stability is often hinted at through words like core, critical, fixed, always on, or conversely, through words like bursty, scale out, ephemeral, or elastic. When you listen for those cues, the address type choice becomes much easier. As a review prompt, imagine a constraint-driven choice and select the addressing type that best fits, because the exam often frames this as a trade-off rather than a direct question. If the constraint is rapid scaling and frequent replacement of instances, dynamic addressing is usually the better fit because it avoids manual coordination and supports automation. If the constraint is strict firewall policy and the need for consistent monitoring targets, static addressing is often the better fit because it supports stable references. If the constraint includes minimal operational overhead with many end-user devices, dynamic addressing is usually the better fit because manual assignment does not scale. If the constraint includes integration with external partners that need stable allow rules, static addressing at the controlled edge is often the practical choice, even if internal components remain dynamic. The key is to align the choice with what must not break in the scenario, because addressing should serve the design priority rather than becoming its own goal. To close the core with a rehearsal prompt, size subnets for 2 zones in a way that reflects blast radius and growth rather than simply maximizing address count. Imagine one zone is a screened application zone that needs room for scale but should be isolated from other internal segments, and the other zone is a management zone that should remain small and tightly controlled. You would allocate enough addresses to the application zone to handle expected growth and spikes without forcing immediate redesign, while keeping it bounded so that policy remains clear and lateral movement is constrained. You would allocate a smaller range to the management zone because fewer systems should live there, and tighter boundaries make auditing and control easier. The exercise is not about exact arithmetic. It is about practicing the habit of matching subnet size to purpose and growth expectations. When you can do this mentally, you will recognize exam answers that either overallocate wastefully or underallocate in a way that guarantees painful rework. In the conclusion of Episode 8, titled IPv4 Addressing Strategy, Public/Private, Static/Dynamic, and Design Implications, the main takeaway is that planning the address space is planning the control plane for routing, segmentation, and troubleshooting. You understand the placement patterns for public and private addressing, and you match static assignment to stable infrastructure dependencies while matching dynamic assignment to clients and elastic workloads. You use subnet boundaries to align with zones and blast radius goals, and you plan for growth, mergers, and multi-site expansion so integration does not become a crisis later. You account for network address translation effects on logging and troubleshooting, and you avoid overlapping private ranges because they break peering and virtual private network designs in predictable ways. Summarize planning steps by starting with zones, reserving space for growth, choosing static where stability is required, and keeping documentation clean. Then assign yourself one addressing plan practice by mentally sketching 2 zones and choosing static or dynamic for each major component. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.